Hello everyone. In this video, we're going to look at the longest consecutive sequence problem. First, we're going to discuss the problem, then we're going to go over 3 solutions, the brute force solution and 2 improved solutions. So for this problem, we're given a list of unique unsorted integers. Our job is to return the length of the longest consecutive sequence of numbers in the list. So for example, if we're given this list of numbers, the longest sequence would be 1, 2, 3, and 4, and that's 4 numbers long. So we would return 4. For this next example, the longest sequence is 7, 8, and 9, and that's 3 numbers long, so we would return 3. If you haven't tried the problem already, now might be a good time to pause the video here and give it a try. Although your first solution might not be your optimal solution, your final goal should be to get the time complexity down to O of n. Okay, assuming you've given it a try, let's go over the solutions. The idea behind our brute force solution is pretty straightforward. We're just going to try all the numbers, and for each number, we're going to see how many more consecutive numbers exist in the list. Let's look at the code. We have our function definition take in nums as input, and we also initialize a max s variable, which stands for the length of the maximum sequence. This is ultimately what we're going to return. Next, we iterate over every number in the list. For each number, we initialize a current max variable, which is the length of the current sequence. We also initialize a next number variable, which will represent the next number in the sequence. While the next number in the sequence is in our list, we increment our current length counter as well as our next number variable. We repeat this process until the next number in the sequence is no longer in the list. Finally, we take the max s sequence to be the max of the current sequence and the existing max sequence, and ultimately we return the max sequence. So this solution is pretty much the definition of brute force, as we're just exhausting every possible number. And let's analyze the time complexity. We have the outer for loop, which runs for n iterations. We then have our inner for loop, which can also run for n iterations. This might lead us to believe our algorithm is n squared, but we have to look at the fact that the while loop condition, while next n in nums, is searching for a number in an unsorted array, which in itself is n steps. So this means our inner while loop is actually on the order of n squared, which means our outer for loop and our overall algorithm is on the order of n cubed. However, we can make one quick fix to make this algorithm n squared. We just use a hash set instead of a list. Looking up if an element exists in a hash set is expected O of 1. So first, converting nums to a hash set, then using the hash set in our while loop condition knocks our time complexity down to quadratic. However, this comes at the cost of n space, which we need to store the hash set. This is a significant improvement, however, it still falls short of our linear time goal. In order to achieve linear time, we have to do something a bit more clever. As I mentioned at the beginning of this video, I'm going to present 2 linear solutions, the one that's commonly found online and the one that I came up with when I was solving the problem the first time. So let's look at how we might arrive at the first solution. Our brute force solution was on the right track, but it did some unnecessary work. Let's see where these unnecessary computations are taking place by looking at this example here. We can see that this example is composed of 2 separate sequences. Sequence 1 is 1 through 5, and sequence 2 is 7 through 9. Let's inspect how our brute force algorithm detects these sequences, specifically with the while loop. When the algorithm encounters the 1, through the while loop, the algorithm counts upwards from 1 to 5. So we actually discovered the first sequence of 5 numbers right off the bat. Next, we move on to the 3, and 3 counts upwards to discover just a partial sequence of 3, 4, and 5. We can begin to observe that this is where our algorithm wastes time, because through the 1, we've already discovered the whole sequence of 1 through 5. So there's really no point in us inspecting the partial sequence of 3 to 5. In the same sense, when we move on to the 5, we'll just inspect this partial sequence of just the 5. And you can hopefully see how, for the 4 and the 2, these also just inspect partial sequences. So we can conclude that the while loop iterations for the numbers 3, 5, 4, and 2 were all wasted time for sequence 1, because we already discovered the whole sequence for the first iteration at the 1. Now for sequence 2, we know that 9 and 8 only discover partial sequences, which again is wasted time. And it's only when we reach the 7 do we discover the whole sequence. So how can we get rid of this wasted time? Well, we need to figure out when and when to not explore a sequence. For this example, we want to explore a sequence when we encounter the 1 or the 7. What do we notice about these numbers? Well, they're at the very beginning of their sequences. So if we only run the while loop if we are at the beginning of a sequence, then we'll never waste time exploring a partial sequence. So the change in our code looks like this. It's literally just one line. In order to detect if a number is at the beginning of a sequence, we just check if the number before it exists in nums. If the number before it exists, it means it's part of a larger sequence, so we can just skip the checking process because we know we'll be wasting our time checking a partial sequence. Therefore, the only time the while loop will run is if we're at the very beginning of a sequence. And this simple modification actually brings our time complexity down to O of n, even though the while loop is nested. Let's see how by tracing through a run of our improved solution. I want to show that even though the while loop is nested, it will only run for a maximum of n iterations, once per number. I can visually show this by giving every number a time life, so to speak, and each number will lose its life if it's inspected by the while loop. So to start, each number is going to have a life. For the first iteration of the for loop, num is equal to 1. Num minus 1, which is 0, is not in our num set, so we enter the if statement and run the while loop. The while loop runs 5 times, incrementing by 1 and discovering the subsequent numbers of 1 through 5. Therefore, the numbers 1 through 5 are going to lose their time lives. Next, we move on to the next iteration of the for loop, where num is equal to 3. We check if num minus 1, which is 2, is in the set, and it is, so this if statement evaluates to false, and we don't enter the while loop. And therefore, no numbers lose their time lives. For the 5, the same thing happens. 5 minus 1 is 4, which is in the hash set, so we skip the if statement along with the while loop. It should make sense that for the rest of the numbers until we reach the 7, this same thing occurs. We skip over the if statement and never run the while loop. Remember, the reason for this is that the algorithm now knows that all these numbers are part of a larger sequence, so we don't want to waste time computing the partial sequence. We want to wait until we encounter the very beginning of a sequence to handle it. It's only when we reach the 7 that the if statement turns true because 6 is not in the list. When we reach the 7 and enter the while loop, the consecutive 8 and 9 lose their lives as well. And finally, our algorithm finishes since the nums for loop is on the last number. So hopefully this time life visual convinces you that the while loop will only be run when a full sequence of numbers are being discovered. And this only occurs when nums is pointing to a number at the start of a sequence. And since there's only one starting point of every sequence, then each number in the sequence will only be touched by the while loop exactly once. So this while loop will only ever run n times over all the iterations of the for loop. For space, just like our brute force solution, our extra space comes from the hash set, which is O of n. So that's the whole idea behind this solution. But before we finish, I just want to add a few takeaways from this problem. The first is to use a hash set to reduce time complexity. If you're experienced in doing these interview type problems, this is probably old news, but inherently this just represents a time-space trade-off. In our problem, we are able to get our initial cubic complexity to quadratic just by first storing our nums array as a hash set. If you ever encounter a problem like this one, where you need to determine if an element exists in a collection of elements or not, you can always make the time-space trade-off and search that unordered collection in O of 1 with a hash set while sacrificing O of n space in order to store that hash set. The second takeaway is to look at where our brute force solution is being redundant and what is the difference between a case that is useful to our final answer and a case where we're just performing redundant work. In this problem, our algorithm was being useful only when it was uncovering an entire sequence and was being redundant if it was uncovering a partial sequence. Once you identify this, try to think of some clever trick or some method through something like dynamic programming to get rid of the redundant computations. In our case, a simple one-line modification was all we needed to reduce our time complexity from quadratic to linear. Well, that concludes this solution, and at this point I'm going to share another O of n solution, which was the one that I came up with when I was solving the problem for the first time. It uses graphs and is definitely messier, and you don't need to stick around and watch it, but I think it demonstrates how the same problem can have two quite different approaches. The idea behind this solution is to have every number in the list be a node in an undirected graph. So for this list of numbers, we would have 8 nodes, and the underlying data structure behind this graph would be a hash map, which would map a node to the set of nodes it's connected to. This is basically an adjacency list representation. So to start off, the underlying map would look something like this, where all the vertices were mapped to empty sets, symbolizing no edge connections in the graph. We want the edges in the graph to represent the consecutive sequence of numbers. So for each number, there can only be an edge connection between it and a number exactly one lower or one higher. In order to construct these relationships, we would iterate through every number and check if that number plus 1 exists in the graph. So for example, with 1, we would check if 2 was in the graph. Since the 2 does exist, we would add an edge between 1 and 2. For 3, 3 plus 1 is 4, and since the 4 does exist, we would connect 3 and 4. For the 5, we would check if 6 exists, and since it doesn't, there's nothing to do because we can't connect the 5 to a non-existent 6. For the 4, 4 plus 1 is 5, and 5 is in the graph, so we would connect them. For the 2, we would connect the 2 to the 3, and ultimately we would end up with a graph like this. Notice how the sequence make up the connected components. Since these add edge operations boil down to just adding elements to a hash set, these can be done in O of 1 time per edge, so ultimately the construction of the graph can be done in O of n time. Finally, we just run a depth first search on all the components and count up the length of each sequence, ultimately returning the longest sequence. If you don't know what a depth first search is, I would recommend watching my video on it, which I'll link in the description. DFS's running time is O of v plus e, but we know the amount of edges has to be less than the amount of vertices in this graph, so therefore we can say the DFS on this graph is O of v, which is O of n. Ultimately, this is what the code ends up looking like. Like I said, pretty messy, and the first improved solution is definitely simpler and easier. I think the key takeaway from this solution is that just because the problem you get doesn't explicitly use a graph, that doesn't mean you can't use a graph in your solutions. Graphs can come in handy in modeling groupings and relationships between elements. In our case here, each element was a number, and we modeled a number's existence with a node. And the relationship was whether numbers were consecutive, and we modeled this relationship with the connection of an edge. So next time you see a problem with relationships and elements, you might try to model this with a graph and see if it leads to a good solution. Anyway, that brings us to the end of this video. If you found it useful, please consider liking the video and subscribing to the channel. All the support really helps. Thank you for watching, and I'll see you guys in the next video.